Hello, and welcome back to Shiksha DaCosta. Today we're going to solve unfactorable quadratics. So today we're going to learn how to solve a quadratic equation when factoring fails us. And these are your curriculum expectations. So today you're going to explore the algebraic development of something called the quadratic formula, and then you'll apply that formula to solve quadratics using technology. The solutions are the real roots of a quadratic equation, and you're going to relate those to the x-intercepts of the graph that connects with it, and you're going to connect the number of roots that you find to the value of something new called the discriminant. Finally, you're going to determine what are the real roots of all sorts of quadratic equations, and you're going to be able to describe the advantages and disadvantages of whatever strategy you used to determine those. To start off, quadratics in vertex form are really easy to isolate x. If we have a quadratic in vertex form, it's super easy to find that value of x. All we have to do is use that isolating strategy of the opposite operation. What we're going to do is use a strategy called completing the square to take a quadratic that is in standard form and turn it into vertex form so that we can then isolate x to find the roots. The first step in this is actually quite a lengthy, complicated process, completing the square, and I kind of hate it. But we do have to know how to use it so that we can see how we can make our lives a lot easier by giving ourselves the chance to experience just a little bit of pain right now. But without any further ado, let's complete the square. So here we have this equation, 3x squared plus 15x plus 18. We're going to factor out just the a value, and we're going to factor it out of just the first two terms by grouping. We're going to leave the last term alone. So I'm going to put two brackets around here and factor out the 3, and 15 divided by 3 is 5. Then I'm going to take the coefficient of this second term that is inside the bracket. So I'm going to take the number 5. I'm going to divide it by 2, and then I'm going to square whatever I get as my answer. So 5 divided by 2, and all of that squared is actually 2.5 squared, and that is 6.25. And this number, I'm going to add and subtract it inside these brackets. So I'm going to put it in just like this. Now notice, because I added and subtracted the same number, I haven't actually changed the value of this equation. I basically added 0. The reason that I did this is because these three together form a perfect square trinomial, and that's why this is called completing the square. But I don't really like this guy in here, so I'm going to actually distribute this 3, or in fact, I'm just going to factor this. I'm going to remove this from the brackets, and I'm going to do that by multiplying it by 3. So the third step is to take this subtracted value out of the brackets, and to do that, we have to multiply it by a. In that case, it would turn into negative 18.75. And I've put it in the back here. Now, like I mentioned, these three form a perfect square trinomial, which is super easy to factor. It will always be x plus whatever half of this number is, which I already know is 2.5. X plus that, all squared. At the same time, though, I will also combine these two like terms at the end here. So this would turn into x plus 2.5 squared, like I mentioned, and 18 minus 18.75 is negative 0.75. That's how you take a quadratic from standard form and turn it into vertex form. This process is called completing the square. The next step in this starting exercise is to find the root. So when does this actually equal 0? To do that, because this is in vertex form, we can isolate x quite easily. So all we have to do is do the opposite operations in reverse BEDMAS order to both sides. So the first one I'll get rid of is the 0.75 by doing the opposite of subtracting, adding. Then I have to do the same thing to the other side. Then I'll get rid of the 3. This is being multiplied, so I will divide both sides by 3, and that will remove it from here. 0.75 divided by 3 is 0.25, obviously. And now I'm going to get rid of the square. And the opposite of a square is a square root. So the square root of this would just cancel that square out. And I have to do the same thing to the other side. And the square root of 0.25 is positive or negative 0.5. So I have to put that plus or minus sign here. When you're isolating and you're removing a square, this is incredibly important to keep, because this is very key to understanding that there could be two different answers, as we'll see in just a second. The last step is removing this 2.5 by subtracting, and then I'd have to subtract on this side as well. So what does this mean? It means positive 0.5 minus 2.5 is a solution and negative 0.5 minus 2.5. The positive version is negative 2, and if I take negative 0.5 and I subtract 2.5, I would get negative 3. So these are our two solutions, or our two roots of this quadratic expression, which is the same thing as the roots of this quadratic expression. And you can plug that into Desmos if you would like to confirm that. Now, the reason we're doing this, okay, we had a quadratic in standard form in its most simplified version. And by doing this process, this allows us to turn it into vertex form and then isolate x to find our solution. So we never really have to factor anything. And that has an advantage because that what this means is we can follow the exact same steps whether there are numbers or whether there are no numbers. So whether we have a quadratic in just its standard form and we have no idea what A, B, and C actually are. What if we actually tried to solve that? What if we tried to find the roots of a quadratic even though we have no numbers? That is the development of the quadratic formula. So I'm going to solve this without any numbers being there for A, B, and C. I'm just going to use algebra rules. The first step was, of course, to complete the square to turn this into vertex form, and that's not easy. This was our equation. And remember, to complete the square, the first thing we have to do is factor A out of the first two terms. So I have to divide both of them by A, and B divided by A is, I don't know what number it is, but I'll just express it as B over A. Then I have to take that number divided by 2 and then square it. And then I'll take this number, whatever, again, I don't know what it is, but I just have an algebraic expression that represents that number. In the past, it was like 6.25. Now I have no idea what it is, but whatever it is, I'm going to add it and I'm going to subtract it inside these brackets. Then I have to remove it from the brackets, but to remove it, I have to multiply by A, right? So I have to take that out of the brackets. And then I have to keep A in front there. And then finally, remember, this factors into a perfect square trinomial. It's just going to be x plus b over 2a squared. And this I'm just going to treat this like one single number. This is my the constant at the end of the vertex form of a quadratic. And this is actually a quadratic in vertex form. If we treat this like one number, and we treat this like one number, it looks exactly like it did before. Now we have to find out, when does this equal 0? So when does this equal 0? Well, here are my steps for how I did it last time. All I did was I did the opposite operation to one side, and I had to do the same thing to the other side in reverse BEDMAS order. So if I have this expression, the first thing I did was get rid of this number on the end here by doing the opposite of whatever the operation is. And over here, it's adding this entire number, so I will subtract it. And because that'll cancel out, I have to also subtract it on the other side. And I end up with an expression that looks like this. Don't get intimidated by all the letters and stuff. We know that this is just going to evaluate to be some number, just like it was over here. The next step is I divided both sides by the coefficient here, which was A. So I'll divide both sides by that number, and that'll cancel it out on this side. My next step is I took the square root of both sides. That canceled out the square over here, and then I had to take the square root of this side. And remember, my answer ended up being a positive or a negative, so I'll write that down. And my last step was to get rid of this, and so I'll subtract b over 2a, and I'll have to do the same thing to the other side. And these are all the solutions to any quadratic that looks like ax squared plus bx plus c. All we have to do is plug in a, b, and c into this expression. Notice the only variables in here are a's, b's, and c's. So we just need to plug it in and evaluate. This could be called the quadratic formula, but it's actually still really ugly. Like, look at this. There's a's all over. There's 1, 2, 3, 4 a's. There's 2 b's. There's a c there. There's a negative inside a lot of brackets. We're going to see if we can simplify it so that later on, when we just want to plug in numbers, we're not plugging them in all over the place, and we're not repeating any work that we can avoid now. So this is the quadratic formula. I'm going to try simplifying this part first. So this is b over 2a squared, which means we're multiplying it by itself. b times b is b squared. 2a times 2a is 4a squared. So I'm going to replace this with b squared over 4a squared. Now I'm going to distribute that a. So I'm going to multiply that negative a into here. So negative a times this. The numerator is multiplied, the denominator is multiplied, and I'm left. And the a squareds in this case, one of the a's in the numerator will cancel out with one of the two a's in the denominator, and I'll be left with just 4a in the denominator. So I have b squared minus 4a now. Okay, that's a little simpler than this. The next thing I'm going to focus on is this entire numerator. I don't like that it's negative. It's all being made negative. I'd rather distribute that negative inside. So negative times c is negative c, and negative times all of this would turn that into a positive. But now I'm actually going to combine these two. How do I take a number and add a fraction? I need the same denominator. And right now, this has a denominator of 1. And so I can multiply that by 4a over 4a, and that will turn the denominator into this denominator, which is 4a. And negative c times 4a is negative 4ac. Now that they have the same denominator, I can just add their numerators. And now I've turned this into this, which kind of made it seem a little bit uglier. But I know if I keep working, I can make it simple. My next step is to focus on this portion right here. So if I'm dividing by a number, that means I'm multiplying by the reciprocal of that number. And the numerator times 1 will just stay the same. The denominator will be 4 times a is 4a squared. And now I'm going to focus on this part right here, the positive or negative square root of that. How can I simplify this? Well, one rule of square roots, which you may not know, and I don't think you need to know this too much, is that a square root of a fraction is equal to the square root of the top and the square root of the bottom, divided by the square root of the bottom. And so I can split that square root up just like that. And the square root of 4a squared, well, that's the same. I'm just going to apply the same rule to square root both of these. So the square root of 4 is 2, and the square root of a squared is just a. And now it's starting to look a little bit cleaner. Can I actually subtract these? They have the same denominator, so I could just subtract their numerators. And in fact, the regular version of the quadratic formula is exactly this, except they've taken this negative b and moved it out front. To get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we have any quadratic that is in the form ax squared plus bx plus c, we can plug a, b, and c into here and evaluate this, and those are our solutions. Those are our zeros. In this lesson, we learned that the roots of a quadratic equation can be of the form ax squared plus bx plus c can be determined by using the quadratic formula, which is given to you here. The quadratic formula gives us a way to calculate the roots of a quadratic equation without needing to graph it or even factor it, because we know that some quadratic equations are not factorable. You can solve quadratic equations by isolating, and you don't need the quadratic equation, the quadratic formula, if the equation is in vertex form, like we did in this lesson, or if there's no x term, then it's usually pretty easy to do then as well. All we have to do is isolate x. The zeros of ax squared plus bx plus c are just the solutions to when does that equal 0, which means we can use the quadratic formula for that as well. In this example, I'm going to solve this quadratic equation. Now, I only know how to solve quadratics when they're equal to 0, so I will subtract 5 from both sides, and now I have an identical quadratic equation whose solutions are the same as these solutions. Now, I'm not even going to try to factor this. I'm just going to use the quadratic formula because that's what we're practicing today. And so I've got negative 2x squared, that's my a value. Negative 11 is my b value, and a negative 3 is my c value. So I'll just plug those in here, and I'll start evaluating. Negative 11 is 11. Negative 11 times itself is 121. And 4 times negative 2 times negative 3 is 24. 2 times negative 2 is negative 4. Okay, so now let's simplify from here. 121 minus 24 is 97. And so I've split this equation up now into two equations, the positive and the negative. And in my calculator, I'll just punch in 11 plus root 97 over -4, and that gives me about -5.2122 with many, many more decimals after that. And I'm going to round that to about -5.212. In this case, I'm going to do the exact same thing, except I'm going to put the minus instead of the plus, and I get a different answer. And this one I'm going to round to -0.288 to the nearest thousandth. And there we go, folks. Those two are your solutions to this equation, and they are the roots of this expression. In this example, I'm going to solve 2x squared minus 5 equals x. So I only know how to solve quadratic equations. This is quadratic because of the x squared. When one side equals 0, so I'm going to get rid of x on this side and subtract it on this side as well, because I have to do that to keep it equal. And now I have a quadratic equation in the form ax squared plus bx plus c. Let's see if we can solve this by factoring before I try to pull out the quadratic equation. So 2 times -5 is -10. The factors of -10 are 1 times -10. Note that doesn't give us -1. That gives us -9. 2 times -5, 2 plus -5 gives us -3. We were looking for -1. And there are no more factors to test. I could switch the negative to these sides, but I'll still get 9 and 3. And I was looking for -1. That would tell me that this quadratic is not factorable. So I have to use the quadratic equation. Thankfully, though, it's pretty easy to use. And when I have a quadratic in this form, all I have to do is recognize that 2 is the value of A, -1, that's the value of B, and -5 is the value of C. So I'll plug those in here. -1 is +1, -1 squared is 1, and -4 times 2 times -5 is +40. 1 plus 40 is 41. And so my solutions here are 1 plus root 41 over 4 and 1 minus root 41 over 4. This would give me about 1.85, and this would give me about -1.35. And to confirm that these actually are true, that these are the zeros of this equation, let's take a look at a graph. This here is the graph of exactly this equation. And notice when I click on the two zeros on my graphing software, I can see exactly these values appear. One thing to learn about the quadratic formula is it doesn't always give you two solutions. The number of solutions you get depends on the value of what you are square rooting. This expression in here, b squared minus 4ac, is special. It's called something called the discriminant. This number is being square rooted. So if this number ends up being a negative number, well, we can't square root a negative. There's the square root of x is not defined. We have no definition for it if that value of x is less than 0, if it's negative. So it actually might have no solutions at all. And that makes sense. Imagine if this quadratic was actually like over here. And I was like, where are the zeros of this quadratic? You'd be like, well, there's none. It doesn't cross the x-axis at all. Sometimes you could have maybe one solution. For example, if a quadratic looked something like that, where it just touches the x-axis at its vertex. That happens when we square root this and only get one answer, not two. And that only happens when the discriminant is equal to 0. Because the square root of 0, well, that's just 0. Positive and negative 0 are the same number. But if this value is positive, like we saw, then there will always be two solutions, since the square root of x squared could be either positive x or negative x. And that's where that plus or minus sign comes from. In this example, we're going to find out when does x squared minus 15x equal -56.25. Well, again, I only know how to solve quadratics when one side is equal to 0, so I'll add 56.25 to both sides and make that equal 0. And now those are my values of a, b, and c, which I'm going to plug into my quadratic formula. That's b, that's a, and that's c. This ends up being 15 plus or minus the square root of 225. Oh, this is 225, and this ends up being 225 as well, which gives me 15 plus or minus the square root of 0. The square root of 0 is just 0, so 15 plus 0 or 15 minus 0 will always give me 7.5 exactly. Notice both solutions ended up being the exact same. That's what I mean. When the discriminant is 0, there will only be one square root, which is equal to exactly 0. So there will only end up being one solution, or both your solutions will end up being the exact same number. And on a graph, that looks like this. This is the exact expression here. And we've graphed it, and you can see that it only has one root. Before I send you off here, a few lessons ago we discussed using a flowchart to factor quadratics, and then that allows us to choose the best factoring strategy to solve it. But if all of these fail, we need one more option. The flowchart goes, is it a difference of squares? If yes, then just use the difference of squares formula. If no, check if the a value is 1. Does it look like this? If it does, then just use the sum product rule, and it's pretty quick. If it doesn't, check if it's a perfect square trinomial. If the first and last numbers are square numbers, and the middle number is 2 times the square root of these two values, then just use the perfect square trinomial factoring to find your factors. But if it's not a perfect square, you have to check, are there two factors of a times c that add up to b? If there are, you can use decomposition. If not, then your only option is to use the quadratic formula. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.